So what calculus is interested in is an instantaneous rate of change. So for example, as you're driving from here to Portage, you're going to stop at stoplights before you get to the perimeter. Well, even after the perimeter, there's some lights, and then you're going to get on the highway and you're going to increase your speed to 110, which is the speed limit, or maybe you like to always drive a little bit faster, 111 or 112. And the instantaneous rate of change would be at a specific point looking at your speed. How fast are you going at that point? Whereas an average rate of change would say, if it took you an hour to travel 75 kilometers from here to Portage la Prairie, then on average you're going 75 kilometers per hour. So we have two different kinds of lines. We have tangent lines, which cut a curve at one point, and secant lines, which cut a curve at 2 points. So if you had a parabola, when we say a tangent line cutting a curve, it's just, most often it just touches that curve sort of like on the outside. And the same way when you learned about tangents to circles in grade 9, they just touch the circle. We don't talk about a tangent cutting a curve like that. That would not be a tangent line. A secant line is when you have 2 points on the curve and draw the line through them. Now the reason we use cut the curve at one point is there is some situations where a tangent line touches the curve like this and actually goes through it. An example would be the x cubed graph. At this point, actually the tangent cuts through perfectly like that. Yes? There isn't any relation that to the secant graph or the tangent graph. They're just called tangent line and a secant line. Well, there might be, but not that's coming to my mind. That's clear right at this moment. So if you have 2 points, and we have it on a circle, but if we have 2 points on any function, and if I kept A the same and kept moving B closer and closer to A, if you kept getting closer and closer and closer, we would say the secant line is the average rate of change between 2 points. But as we get closer and closer to the points being the same, your secant line turns into your tangent line. And the slope of that secant line gets really, really close to the slope of your tangent line. So I've got an applet here on the internet that does it with a parabola. So here we've got a parabola, and right now the red line is a secant line. And I can take this point and I can, I can go to my computer and take that point, there we go, and drag it closer. And as I get closer and closer and closer, can you see that the secant line is becoming closer and closer to a tangent line? So we calculate slope by doing rise over run. And right now, the rise over the run, which is showed up here, is the slope of my secant line. As I get closer and closer, so right now you can see right here, the slope is 1.4. And as I get closer and closer and closer and closer, the slope is approaching a number. Don't breathe. Slow. Closer. Oh. And so we might estimate here, because the slope is at 0.614, maybe this slope is going to become 0.61, or maybe it's 0.60. And then that would be the slope of the tangent line. So what our job is going to be, what we're going to want to do, so if we have y equals x squared plus 1, and you take a point on this line like 1, 2, and you drew a tangent, we would want to find what's the slope of that tangent. And some of you already know, you've done a little bit of calculus already, can say, oh, I can just look at that equation and be able to figure out the slope is 2. For those of you that haven't looked into the calculus yet, you're like, well, how do we figure that out? Why does that work? And that's where we're going to. So as we get closer and closer, if we take the vertex, you would say the secant line becomes closer and closer to becoming a horizontal line, okay? And becomes the tangent line at y equals 1. Now, according to the definition of cutting through the line, you could cut through the line at y equals 1 and x equals 0, but our tangent would be just the line that is flat. It's like touching that line, because your tangent line is the slope of the secant as they get closer and closer. So if you imagine having 2 points really, really close together and drawing a line through them, that would be a secant line, and it would be really, really close to the tangent line. So when you're wondering, well, which way should that tangent cut through the curve, you can imagine just drawing 2 points really close together and drawing them. So that's our tangent line, a line that touches a curve at one point and whose slope or gradient is equal to that of the curve at that point. So here's a diagram, and this could be a parabola, this could be an exponential function. Here's a diagram of what's happening. We've got a point A, which we're just going to call x comma y, or x comma f of x. Then we add a certain horizontal distance, h, and then we would have another point. If this point is x and this is h, does it make sense that this point is x coordinate is x plus h? And if this is my function and this is my y, f of x, this would be my y here, f of x plus h. And so the slope of this secant line is rise over run. F of x plus h minus f of x, that would be my rise. Does that make sense? Take this number on the top, subtract this number on the bottom. And my run would be take this number, my x coordinate of b, subtract my x coordinate of a, which would be h, that distance. And so the slope is just f of x plus h minus f of x, that's my rise, all divided by h. What do we need to do to h to make the secant line closer to a tangent line? Move it closer. And what would happen to h as we moved it closer? It would approach 0. And so our definition of our derivative is we say, let's make h get close to 0. And if we do that, we create a limit. Say, what happens is a limit goes of h goes to 0 of f of x plus h minus f of x divided by h. And what we get is the definition of the derivative. Because what the definition of the derivative is just trying to find that slope of that tangent line. And that's like our first unit of calculus. Done. You just have to figure everything else out from there. Easy. But that's the big idea. Derivatives are about finding the slopes of tangent lines so we can find instantaneous rates of change. How fast things are changing at a moment. And they're found by taking the slope of a secant line and making it the points come closer and closer until it becomes a tangent line. So this part here says limit as h goes to 0. If we go back to our diagram, here's our value of h. We want to make that get closer to 0. We would do that by dragging this point along here closer and closer. Can you see that if I have them that close together and I drew a secant line, it'd be very close to my tangent line, and my h value would be small. But then you'd go, oh, I don't know if that's small enough. I want to move it even closer. And move it even closer and move it even closer. And if we look at what that limit does, we can get the slope of the tangent line. The powerful thing about calculus is we're going to find for something like y equals x squared, we're not only going to find the slope for specific points, we're going to find the slope for the whole function. And we're going to find out that the derivative for this one is going to be 2x. We're going to find out a derivative function. And what this derivative function says, here's my x squared graph. If I took a point like 2, 4, and I drew a tangent on there, if I look at my derivative, y prime equals 2x. When x is 2, what's 2 times 2? The slope of this line would be 4. If I picked another point, negative 3, 9, and I drew a tangent on there, I could tell that the slope of that tangent will be negative 6. So part of our question is, how do we do this? How do we go from there to there, algebraically? How do we use this definition of a limit to figure that out? So this formula is known as Newton's quotients, or first principles of the derivative, or the definition of the derivative. And if you use that, you can find a new function called the gradient function, or the derivative. And like I showed in the example before, if you want to find the slope of the tangent at a certain point, you can use that new function that you found and plug in the point to find the slope. Here's some notations for derivatives. F prime of x, y prime of x, or y prime, and Leibniz notation, dy dx. So there's two main notations because there's the notation that Newton used, which is f prime, and there's the notation that Leibniz used. And it's kind of neat because some notations are nice in one place, but not nice in another place, and vice versa, so they're actually both quite useful. Okay, this is where we're going to stop. So we're going to, next class, figure out how to use Newton's quotient,